All right, recording is rolling. It's Friday, October 8th. Welcome to class, everybody. So you guys remember yesterday we went through a bunch of textbook problems and we got through most of them, but there was one I skipped. And the reason I skipped is because I have to go in and fill in those details right now. Actually, I got to get you guys. Do you guys see a quarter page like this on some of the desks? Let me hand this out real fast. I have this ready for you guys. Go ahead and pass these back. This is, let me throw one up here and talk about it for the video while I'm passing this out. Okay. So, you guys start talking about rotational kinematic motion a bit. Again, I usually teach this class in a little bit different order, usually taught this by this point, but we're going to look at what's the physics of like rotating in terms of kinematic motion. So, well, time is still going to be time, you're taking along, but this page shows you linear motion variables and rotational equivalents. So, for example, instead of being interested in how far has something moved in meters, now we're going to be interested in how far something turned, and I'm saying in radians, so radians. But there's actually at least 3 different ways to measure this. You could measure how far something turned in degrees. You can measure it in revolutions, right? But the reason I like radians, what you guys are going to see by the end of class, is because when you apply equations, that's actually the best version for equations. Right, so I've got a turntable right here. I got some coins parked on this turntable. Right? Let's give this thing a spin and think about the mechanics of what's going on. Okay? So get rid of this Roosevelt. So we've got these 3 Roosevelts. One's near the center of the rotation, and then this guy's, well, they're getting further and further out. Okay? Now, would you say that all these coins have the same like turns per time, right? Like the same revolutions per minute? You guys have heard revolutions per minute, right? Like RPM. That's one way to measure. This next value down. It's called omega. That looks like a curly looking W. That's Greek letter omega. It's going to represent angular velocity in 8 radians per second. Right? Like how fast is something spinning? Right? Do they all have the same linear velocity? Like if you point a radar gun at every one of those, do they have the same linear velocity? No. So which coin is going the fastest? Yeah, the one on the outside. If you're talking about linear velocity, but what about the other one? What about angular velocity, like omega? Do they all have the same turn per time? Oh, that's the same. Huh. So interesting. We got these 2 different ways to think about velocity now, and they. And so, depending on what we're talking about, linear velocity or angular velocity, it's actually 2 different things going on. Right? So, once we got here, there's how far something turned. We're going to use theta. Hey, kind of like measuring like an angle, right? You can measure in degrees or revolutions, but when I get to the equations, I'm going to be using radians, and you'll see why when we start applying it. Okay? There's omega. How fast is something turning? Call that angular velocity in radians per second. And hey, could I do this? Could I spin this faster and faster and faster, like speeding up spinning? Or if it is spinning, I could let it go and it like slows to a stop. Do you think there's some rate change associated with that might be like, like maybe radians per second squared? Right? That's called angular acceleration. And we're going to use Greek letter alpha for that. Now, you guys have seen this character before. We've used it in the past to represent angles. Sometimes you see it for angles. This is not that. This is a different context. So, I mean, there's only so many letters to go around. So, run out of Latin letters, you can use Greek letters, and then start recycling them. So, in this context, it could be like angular acceleration. Okay. So, I need to give you guys, and then what about the other values on this quarter page? So, there's some down here. There's a rotational equivalent of mass, which is called rotational inertia. F equals ma has a rotational equivalent that involves something called torque. And then there's stuff that involves momentum that we haven't even talked about in this class. We're going to save those last 3 lines for in the future, so that'll all come back. But just for today, we're looking at the first few lines, and I'm going to give you guys some notes based on that. All right, we'll go back and hit that textbook problem after I give you guys the notes, and then we'll end today on a Kahoot. Then I'll get you guys your MTV news. Yeah, that is the plan. All right, so suppose I got a This is sort of a here. Yeah. Let's do, what's this? Okay. So I'm going to have a symbol. There's going to it's going to have a name. It's going to represent some variable. And then there's going to be an associated unit for rotational kinematic motion. It's sort of a table here. So there's Greek letter theta that represents angular displacement. And you could measure that in degrees or revolutions, which would be common ways to do it. But like I said, when we get to the actual equations, we're going to be using radians. And I'll show you in a few minutes what 1 radian is. Oh, I'm so sorry. Let me back up so you guys can see what I'm writing. I'll show you guys in a few minutes what 1 radian is. You probably learned this in a math class, but we'll come back to that idea. There's how fast is something spinning. That's called omega. That's angular velocity. The adjective angular is interchangeable with rotational. So if they said like rotational velocity, rotational speed, same idea. That's in radians per second. How fast is something spinning? And then you could go, a rate change of that could be alpha, angular acceleration. That'd be some change in radians per second per passing second, which is called radians per second squared. Kind of like meters per second squared, but now it's radians per second squared, like rotating. Right? So we got a circle going. So got a circle. The circle has some radius called r. And if I start trekking around the circle, well, do you guys know a formula that could tell you 1 trip full around the circle? Ooh, that would be called the what of the circle? Circumference. And what is circumference of the circle in terms of its radius? 2 pi r. I'm going to show you guys that this is actually part of a larger general formula that, so we're getting there. Okay. But I need to tell you guys what 1 radian means. So like as a unit of rotation. Okay. So see this radial size? What if I turn this into a string and I take that string, just snip it out and go start wrapping it around? You think it'd probably get about right there-ish, probably about that far. Okay. So we mark that distance out. So this distance right here is also r, right? Just up to this point. Okay. Now, if that's true, then this angle is a very special angle. It's called, what do you think it's called? 1 radian. 1 radian. Okay. And you guys told me how far it is all the way around the circle. And I want to put these two ideas together right now so you guys can tell me about how many degrees is 1 radian. Can anybody figure that out? Can you guys beat me to the answer? Because you guys know it's 360 degrees in the full circle. And it's also, you guys see it's going to be like 2 pi radians to go around? Right. Oh, I'm so sorry. I need to give you guys one little detail to put this all together. Okay. And that's, you can actually translate between rotational values and linear values. Let's go back to these coins. Now, I'll show you guys what I mean. Okay. So if you want to say, how far has one of these Roosevelts gone? Well, you guys see if you park one of these Roosevelts right on the center, that it doesn't matter how fast it's spinning or how long it's been spinning for. It just has zero distance moved. Okay. But the further out you get, see how there's like further and further distance, right? And I'll tell you guys how you can translate back and forth between how far you've turned and how far distance that you've moved. And it's this right here. How far you've moved is equal to how far you've turned multiplied by your distance from the center. Okay. Okay. Now the catch is that this rotation distance is only measured in radians. So I'll say in radians. And then r might be in like in meters or centimeters or something, right? Okay. Hey, look at this. Do you guys see that circumference equals 2 pi r is actually one specific application of this more general formula, right? Because if you know your radial distance from the center and you want to get one exact trip around the circle, that would correspond to 2 pi radians. You guys see that it would take 2 pi radians to make one complete trip around? Okay, so now let's go back and revisit that question that I was asking you guys. How many degrees approximately would 1 radian be? Can you guys figure that out?
Pi over 180.
Yeah, it is pi over, or hold on, I think the reciprocal back, right? Like 180 over pi. Yeah, that's what it is, right? Or you might take 360 degrees and divide by the full 2 pi. Right. Either way you do it, you'll get about 57 degrees. So this is approximately, although not exactly, but just kind of pretty close benchmark. 57 degrees. Right. You guys know what a 60 degree angle is. It's actually 57.2957 something. Okay. Pretty close. Okay. You know what? Do you guys think there's also a way to relate angular velocity to linear velocity? Okay. Like these speeds, right? Like the middle one has what speed? 0 meters per second. Right? But the further out you get, the faster you're going. Like if I point a radar gun at them. Okay? Do you guys think that you could say divide both sides of this equation by time and get something like, hey, what is x over t? That's v. And then what is theta over t? Well, that's omega, right? Radians per second. Multiplied by your radial distance from center. Oh, now we got another expression. How fast are you moving as a function of how fast are you spinning and where are you located from the center? Okay. Do you guys think you could finish this out with acceleration also and say that your linear acceleration is equal to your angular acceleration multiplied by your radial distance from the center? Right? Now you have a way to translate back and forth between these kinematic values. I do want to emphasize that centripetal acceleration and angular acceleration are two totally different things. Right? I've just seen students mix these up before, and it's just one of those things that like, oh, it never even occurred to me that somebody might mix these up. They have different units. Like centripetal acceleration is in meters per second squared. Angular acceleration is radians per second squared. So it's totally different concepts. Okay. Remember, centripetal acceleration is what's the acceleration like center that points to the center of the circle, like to be in a circle. Angular acceleration is if you're spinning faster or slower, like if you're speeding up or slowing down spinning. Okay, so different ideas. Okay. I want to make another connection between linear kinematic motion and rotational kinematic motion. It goes like this. You guys remember those 3 kinematic formulas that you see on that green poster over there? And the top one goes like this: x equals v naught t plus half at squared. Like you guys remember that, right? You know what? If you plug in the rotational equivalents of every single one of those linear motion variables, you actually get a perfectly valid rotational kinematic equation. For example, instead of how far in meters, you might say how far something turned in radians is equal to omega naught t plus half alpha t squared. Like time is still time, so that one stays the same. But the other ones, yeah, you plug in the rotational equivalents. You guys see how you can start making these relationships? Just for completion, I'll do the other 2. So omega final squared, just omega final equals omega naught plus alpha t. And omega final squared is equal to omega initial squared plus 2 alpha theta. So, hey, there's the 3 kinematic equations, but in a rotational context, right? So something to do with like spinning. If there's an alpha involved, it might be speeding up or slowing down. Okay. Guess what that? Okay. Now, how would this relate to, say, centripetal force, centripetal acceleration? Like I was making the point that that's a separate concept from alpha, but how does that tie to this? Because, I mean, if something's rotating, there's got to be a centripetal force to keep it in a circle. Right, so let's go back and look at a circle and see if we can figure out these dynamics. So have a circle. There's the center, and maybe I got one of these coins like right on the radial edge of the circle, so some distance r from the center. Okay. And I'm going to give this turntable a spin. I can measure that spin as some omega value, radians per second. So if there's an instantaneous speed like this for that coin, but of course that immediately changes direction. It might be a constant speed, but so it changes direction. Okay. Okay. Therefore, you guys can see this in real time. Just focus on one of these coins as it's going around. Okay? This is what this looks like. Okay? Okay. When this thing is when it's rotating, see this coin right here? This coin on the outside. Okay. Which direction does the net force on the outside coin point? Which direction is the net force? Towards the center, right? Wouldn't that be a centripetal force? Actually, what force is that even? What force is providing the centripetal force? I mean, it's not a tension. It's the what? It's the friction. The friction between the two surfaces, between whatever this applied wood type surfaces and the coin, right? There's a friction force. Let's do a free body diagram. So, right pen. Okay. Let's do free body diagram, okay, for this coin. You guys think that there's a force that points right in towards the center, and it would be a friction force, right? Well, tell you what, this is actually a partial free body diagram because there's two other forces on the coin. It's weight down and it's normal force up, but that's into another page, right? Okay. Right, so I wonder what the forces are, how this links to its rotation. Like for example, you guys know that centripetal force. Let's do both. Let's do centripetal force. Could be mass of the coin times its linear speed squared divided by its radius of curvature. Okay? And if you wanted the acceleration version, could you just divide by mass and get v squared on r? So maybe I'll just split the page and do both these side by side so you can see in terms of force or in terms of acceleration, whichever one you want to think in terms of. I want to relate this to the spin rate. Like, could I figure out each of these knowing like an omega value? Do you guys remember from last page of notes that, remember how the linear speed is equal to spin rate times radial distance, omega r? Hey, could I substitute that in? V equals omega r. Could I take this and substitute it right in there? Okay. And I would get centripetal force then is equal to m times omega r quantity squared over r. Or if you like the acceleration version, you just do omega r squared divided by r. Okay. Do a little cleanup here. So that'd be m omega squared r squared over r, or if you like, omega squared r squared over r. Okay. Oh, one of the r's is going to cancel, isn't it? And that gives you the formulas that I'm getting at here. Centripetal force is m times omega squared times r, or if you like, centripetal acceleration would be just be omega squared times r. Okay. Is that right? Remember the old ways of thinking of was mv squared divided by r, or v squared divided by r, which are also valid. You could do it that way too. But there are some cases where it's actually more handy to have a that version of it, which is actually what we're about to do right now. Guys ready to finish this homework problem? Yeah, this is yes. Okay. You guys good so far? Okay. All right, so your textbook problem, the one that we skipped yesterday, now we can do it because now you guys have the info. Number 16, it has been suggested that rotating cylinders about 10 miles long and 5 miles in diameter be placed in space and used as colonies. I'm going to draw this out for you guys. This is called an O'Neill cylinder. I'll have you guys make one of these one day too. So someday we'll have these space habitats and they'll be rotating and having artificial gravity and show you guys how it works. Okay. The only reason we don't have something like this now is because it's just really expensive to get stuff into space. What angular speed would one of these cylinders? Hey, angular speed. That's omega, isn't it? That's what I just showed you guys. Should one of these cylinders have so that its centripetal acceleration at its surface equals the free fall acceleration of Earth? Why would you want that? Why would you have one of these giant rotating cylinders that's rotating at exactly a speed to have centripetal acceleration the same as free fall on Earth? Why would that be useful? Well, you can probably figure it out anyway, but if you haven't quite caught on, then when I draw this out, you guys will see why. So your textbook said have one of these cylinders give this axis of reason I got a ruler. Draw a straight line. Get a straight line axis of rotation right here. Okay. Like semi-transparent. Okay. What if you had a big old cylinder in space? Now your book said 10 miles long and 5 miles diameter. 10 miles, 10 miles. Okay. I'm going to come back and talk about that in a minute, but so sort of a detail. Okay. Okay. But just for now, just the basic premise. If this has some spin rate, omega, about it, that central axis, okay, then you could be walking around here. This guy's walking around on the surface on the inside. Got some guy over here. Okay. And everybody feels like they're right side up. Okay. That guy right side up. This guy right side up. Okay. You guys see how this is working, right? So this is spinning around this way, and everybody feels like they're right side up. Okay, so hey, do you think that if you spun this really fast, these people will feel really heavy? And if you're spinning too slow, these people will feel really light? If it's not spinning at all, they just be floating around in space. Right? This is in deep space, right? You guys get that? This is called an O'Neill cylinder. Kind of like that. Hey, remember seeing that guy in that centrifuge that got up to like 9 Gs because they were spinning around so fast? But you could use like the same math we're about to do here. Right? But this is in deep space. So deep space. So there's no true gravitational force around. But you could create an artificial gravity force. Like this guy could be sitting in a room, and if you can't see the outside world, it might be really hard to distinguish this artificial gravity, maybe provided by a normal force acting as a centrifugal acceleration. It might be hard to distinguish that from true gravity. Right? Like we could be sitting in a room right now. It'd be really hard to tell. Okay. Now, you guys get the premise of that? Okay. Now, side note here. Your book actually got something kind of wrong here. So see this 5 mile diameter versus this 10 mile length. That is not actually stable, and I'll sort of show you guys why. So some of you guys might know what I'm talking about. You guys got your cell phone? So can you guys flip your cell phone like this? In a stable, yeah, it would just be like a stable axis of rotation, right? So that's fine, you can do that. Can you guys flip your phone like this? Stable axis of rotation? Yeah, you guys can do that too. Right. But I've got a challenge for you guys. I'm going to tell you guys something that I don't think you can do. Okay. All right. Here. All right, get you checked in here. All right. Can you guys take your phone like this and flip it so it makes one complete revolution all the way around like this, one complete rotation? Right. Yeah, I give you guys about 30 seconds to try that while I'm updating this record over here. Can you guys do that?
I can do it and make it like spin.
All right. So you guys having some trouble doing that along that axis? Right. That is called the intermediate axis theorem. Intermediate axis theorem. Right. And it is not. It won't be stable along that axis. Did I ever show you guys a YouTube channel called Veritasium?
Yes.
Yeah. Did you guys see the video where he talks about this? Does this thing is cell phone? Check that out. For this reason, the book version of the O'Neill cylinder actually would not be stable. This would eventually just turn sideways and it would fly out the ends. Yay. So that would be fun. That's why everybody needs to talk to me before they build these things. Yeah, it would actually start rotating about like this axis here. You're like shoo, 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 and all these people like fly off in space. But if you had that, this could work perfectly well as long as you just made it a little bit shorter. So if you had something like this and then had everybody walking around. So that's sort of a side note to this problem, just for fun. But we can still solve this. So it's gonna go. Oh man. All right. So sorry guys, well, okay, we can stop this here. All right, so let's take these distances. You guys see the 10 mile distance actually is going to make no difference at all. It's really diameter we care about. Okay. Let's translate that into metric units. So I'm going to take the 5 miles. Okay. And let's convert that into meters so that we can make sense of this. Okay. So there's, I think this is exactly right. Commerce and no, this is AP would not expect you to memorize this number. So it's 1.61 kilometers in every 1 mile, which, by the way, just complete coincidence, ends up being extremely close to the golden ratio. So that's actually a good approximation. And of course, 1 kilometer is exactly 1,000 meters. Okay. So kilometers, miles. Okay. So how many meters are we talking about? I'm sorry. One more thing. Okay. I don't care about the diameter. I care about the what? Radius. So let's say radius equals, wouldn't that just be 2.5 miles radius, right? 2.5 mile radius. Okay. So 2.5 mile radius. Okay. Let's translate this into meters. That looks like 4,025 meters. Okay. So that's a middle step. That's not the answer yet, but that's a middle step. The question was, what's the rotational velocity of this? What's the angular velocity? So that you would experience Earth gravity right at the edge. And you know what? I just gave you guys remember this right here? Angular acceleration is, centripetal acceleration. I just made a whole deal of different concept. Centripetal acceleration is omega squared times r. You guys remember that? Okay. So let's put this all together. If centripetal acceleration is omega squared times r, and you know what the radial size is, okay. And we're solving for omega such that, hey, what should the centripetal acceleration be for each of these people? 9.8 meters per second squared. Here's the axis of rotation. Here's the very center. Yeah. We'll solve in terms of variables since you guys are AP. So when omega squared be equal to centripetal acceleration divided by r, and then omega is equal to the square root of that. Okay. Now let's plug in the values. So omega is square root of, okay. Let's use the perfect 9.8 meters per second squared because that's the number you guys shout out. Let's do that. And the radial size was 4,025 meters. So 4,025 meters. Okay. So square root 9.8 on 4,025. Okay. I'm looking at 0.049 something radians per second. That is a great question. Is that slow? Because, I mean, that's a tiny decimal in terms of a new unit that you guys probably just learned today. Hey, let's put this in a little bit different context. Can you guys convert this to degrees per second? Do you think you could? Yeah, do a little dimensional analysis. So how many radians, or how many degrees, and what's the conversion from degrees to radians? Yeah, remember it's like 57 degrees per radian. Okay. Yeah, or more exactly, you could say this. There are 2 pi radians in 1 revolution, which is 360 degrees. Okay. Or I think what Arib was saying was there's pi radians in every 180 degrees. If you like that, make it a little shorter. Right? So 0.049 times 360 divided by open parenthesis 2 pi close parenthesis. Okay. You guys see we're about to get degrees per second, right? Degrees per second. So this is also equivalent to 2.8 degrees per second. If you like, so that's a little bit easier maybe to conceptualize. Okay. So basically close to 3 of these tick marks every second. So you see it just like rotating 3 degrees per second. You know? Okay. How long would it take to make 1 complete revolution? So like if these guys are watching the outside world, right? Or let's go with these guys. These guys are having fun in space, but these guys are here. Right? How long would it take to make 1 complete trip around? Well, if they're doing, let's do another conversion type here. Okay. What this? If you're looking for 1 revolution, dimensional analysis, I know 1 rev is 2 pi radians. Actually, maybe you could have started there, 2 pi radians, right? Okay. And they're doing this many radians per second. So that'd be 0.0493 radians per second. Okay. Or I'll tell you guys what, if you started with 360 degrees and you use this number, you would get the same thing, wouldn't you? So 2 pi radians divided by 0.0493 radians per second. I'm looking at 127 seconds, so just over 2 minutes. Okay. So to tie this all together, if you were to one day build an O'Neill cylinder in space that had a diameter of 5 miles, and we did all the conversions on that, then you would need it to make one revolution around this axis in just over 2 minutes, so that if you did all that, exactly that setup, you had to spin that rate, it takes 2 minutes to make one revolution, then these people walking around on the inside would feel like they were in Earth gravity, but it would be artificial gravity. Right? You guys good? And okay, I got one more thing for you guys. Right, you guys ready for one more thing? You guys got your phones? You guys were flipping around? All right, let's do a Kahoot. This is going to be a Kahoot on the inverse square law relationship for universal gravity. So let's pull this up. Hey, come on. Yeah.
How do you convert radians to degrees again?
There are 2 pi radians is one revolution. 360 degrees is also one revolution. So 2 pi radians is equal to 360 degrees. It's
So 2 pi.
okay, where's my, it's on that. Yeah, so 1 revolution equals 2 pi radians equals 360 degrees. It's all the same thing. Oh, whoops. I thought it was, sorry. Let's get classic. Okay, come on. All right, here's your guys' pen. All right, so for this Kahoot, do you guys remember the universal gravity formula? The force between two objects is universal gravity constant times the masses multiplied together divided by the distance squared. You guys remember that? All right, that's what you guys are going to be navigating right now. Okay. And that equation is on a poster hanging in the front of the room. You guys see that? Okay. So just going through that poster. Okay. So most of these questions focus on the inverse square relationship between force and distance, but there's a couple questions that ask, like, what if you were to change the mass, something like that. Okay. All right. Oh, we got Paul Hewitt in the mix. Bumpkus Wilkins, he's joining this class.
No.
Oh, 125 meters. Yeah. Yeah, there's really bad connection in this room. I don't even know how you guys get on the internet in here. All right. The pen will be at the bottom. Need to hop in. All right, so what if you double the distance between two objects? How does the force respond? So if you double the distance, okay. You guys remember I was telling you the analogy with the candlelight? So if you back up twice as far away from the candle, you catch 1/4 of the light, right? Hey, doesn't gravity work the same way? So if you factor 2 squared in the denominator, what's 1 over 2 squared? Isn't that 1 over 4, like a fourth? Yeah, so if you double the distance between two things, you can get 1/4 of the force. Right? You guys see this equation right here? So double the distance, factor 2 squared is 4, 1 over 4. Okay. Right, so most of these questions about like that. We got 125 meters, Ryan and Vinny.
Who joined as me?
So what if you go the other way? What if you cut the distance in half? Now what happens to the force? Hey, isn't this exactly the opposite of what you just saw? Right? Guys, if you throw a factor of 1/2 on this radial size, what is a factor of 1/2 squared? 1/4. What is 1 divided by a fourth? 4. Doesn't it make sense if you're getting closer together, you're getting stronger force? Right? So 4 times the force. 125 meters. Vinny, College. Bumpkin Wilkins. Ryan. What if you double one of the masses but leave everything else the same? If you just double the big mass, what happens to the gravity force? Well, factor 2. Yeah, you guys got that, right? So that doubles the overall force. Ooh, Vinny's on fire. 125 meters. Still leading. Got College,
You, Eddie.
Juliet, and Pumpkin Wilkins.
Oh wait, there's another person named Ryan Russell.
What if
Yeah, I'm not playing.
what if you triple both masses? Guys, what's triple? What if you triple both masses? Triple. What's a factor 3 times another factor 3?
3.
Yeah. All right. You guys getting this? 125 meters. Still leading. What if you quadruple the distance? I guess it's now we're back to distance changing. Right. I'm gonna throw a factor of 4 on this R. That factor of 4 becomes squared. Right? Like you get 4 times as far away from the candle. Right. What's 1 over 4 squared? Ah, 1/16th, right? 1 over 4 squared, 1/16th. So 1/16th of force. You guys probably know. Almost forgot to mention. You guys know that your AP classroom unit 3 multiple choices due Tuesday, right? Some of you guys have already done that. I want to cover that on Tuesday, but you guys have probably done enough of these down. You know, AP likes to ask these kinds of questions too, right? Like, what's the relationships between things? Right. What if you
I'm just trying to.
cut the size into 1/4? Yeah. Hey, you do this for the video. If anybody's still watching the video at home, you guys remember there's some college physics questions that aren't due until next Friday. We're still covering those. And AP Classroom Unit 3 is due it's coming Tuesday, so that can cover those. Yeah. So 1 divided by 1/4 squared, that's 1 divided by 1/16th. That's a factor of 16 times. Get close together, the force is going up, factor of 16. 125 meters. Juliet, Abby, Ryan, Vinny. What if you cut the distance into 1/3? Yeah, 9 times. 9 times the force. 1 over 1/3 squared. That's 1 over 9. That's 9 times. Ooh, somebody happy hopping in the top 5. 125 meters, still leading. What if you triple the distance? One over 3 squared is 1/9. Yeah. Is there any question why it would be anything else? You guys get that? So 1 over 3 squared is 1/9. Right. These last questions, calculator might be handy, maybe not. Right, you guys ready? Right. So last couple. Right. So GMM over R squared, that's the gravity force. Suppose that on Earth you weigh 500 newtons. Right? How much would you weigh on a planet of the exact same mass, but half of Earth's radius? Kind of like we take the Earth and just like squash it down, like compress it. Right? So same mass planet, but physically smaller. I'm going to guide you guys through this one. So half of Earth's radius. Wouldn't that just be throwing a factor of a half on this R? Guys, what is 1/2 squared? 1/4. What's 1 divided by 1/4? 4. Ooh, 4 times. Wait, are you actually getting heavier on the physically smaller planet? Yes, you are, because your distance actually got smaller, isn't it? Doesn't it go by a factor of 4? What's a factor of 4 times 500 newtons? 2,000 newtons. 2,000 newtons. Yeah. You'd actually weigh more on that planet. All right, got 125 meters. Juliet, Abby, Ryan, H. Last question. This is for the winner's podium. Suppose on Earth weigh 900 newtons. How much would you weigh on a planet of the same mass but 3 times Earth radius? Kind of like you puff it up like a giant popcorn kernel. Like poof. So got a giant popcorn. Same mass, just physically larger. Hey, wouldn't that be kind of like if you climbed an extremely tall ladder and got very far away from the center of the earth? It's the same mass beneath you. You're just physically further away. Guys, what's 1 divided by 3 squared? 1/9? 1/9 of 900 newtons? 100 newtons. Oh, yeah. Oh, yeah. With the bronze, Abby. With the silver, Juliet. And with the gold, 125 meters. 125 meters. We got H and Ryan round out the top 5. Hey, nice job, guys. Nice job.
Good job, Brian.